Yeah, in the last lecture we stopped at theorem 4.23. Which is Pearson's theorem. And we had the following statement. We had two operators, A, B. Let A and B be self-adjoint operators in a Hilbert space H with the property that they have the same domain. So the domain of A is equal to the domain of B. Furthermore, we had an operator J, a bounded linear operator on the Hilbert space H, such that the operator C that we defined as AJ minus JB is a trace class operator. This was equation 4.1. And then this theorem says that the strong limits that we defined as omega plus minus of A, B, and J, defined as S limit for T to plus or minus infinity, exponential ITA, J exponential minus ITB, and here we have the projection onto the absolutely continuous subspace with respect to B. Then these strong limits exist. Yeah, and last time we started with a proof. And the proof is subdivided into 4 steps because it's a long proof. There's a lot of pre-work to do. And I would like to recall some things so that the notation is clear for today. Again, we defined in step 1 an operator W of T, which was exponential ITA, J exponential minus ITB. And when you look at the statement here, then it's clear that we are interested in the behavior of W of T applied to a function phi and the limit for T to plus or minus infinity. That's what we are interested in. And to obtain this limit, our aim was to prove the following: the limit for T to plus infinity, let's say, of the supremum for S bigger than T of the difference W of T minus W of S applied to a function phi, and I also take the square of this to be able to do computations, that this is equal to 0 for all phi in this set M of B that we defined. You might recall that this M of B was a subset of HAC of B. It's also dense. And it had the property that for functions belonging to the set, we have that the spectral measure, where this is here the spectral family corresponding to the operator B in this case that we have, that this is given by a density F in this way. And furthermore, and this is the interesting thing, this function F is a bounded function, and it satisfies that its support is contained in such a compact set for R bigger than 0. And we also have that E of R applied to phi is equal to phi, and E of minus R applied to phi is equal to 0. And furthermore, this is what we will also need. We we defined a norm on this space with, in this way, and we defined it simply as the infinity norm of the corresponding function f. Yeah, so we prove this here for a dense subset of HAC of B, and this is exactly what we will need. This is where we stopped last time, and we also found out in step 1 that we have the following identity. Yeah, first of all, we defined an object capital F, AB of x, where x is an operator applied to U. This was the integral from a to b, of course for a smaller than b, of exponential ITB, x exponential minus ITB UDT. And then we found out that that we have the identity W of t star W of s minus exponential I AB W of t star W of s exponential minus I AB, that this object is equal to f with the indices 0 and a of y of t and s, where this was 4.2, where this y was given in the following form, or it has the following form, so to say. Y of t and s was defined as minus I, and then we had exponential ITB. I think this is a little bit dark here. This is better. This was exponential minus IT minus I, and here exponential ITB. Then we had J star, exponential minus I t minus s a. Here the operator C, exponential minus I s b minus the second term exponential ITB. Then C star, exponential minus I t minus s a, j, and exponential minus I s b. Let me check this. Okay, the first one is correct, and the second one, too. Yeah, this is what we achieved in step 1. And then we had seen in step number 2 that we have the identity phi times W star of t, W of t minus W of s phi. We found out that this is equal to the limit for a to infinity of scalar product phi with f 0 a, and here we had y of t and t, and then minus y of t and s applied to phi. This was equation 4.3 that we had seen last time. And then we also started step number 3. The operator C, by our assumption, is trace class. So we know that C has a representation of the following form. It can be written as a sum over n, lambda n, and here a scalar product phi n, psi n, where these singular values lambda n are positive, that's what we can assume, and because of the fact that the operator is trace class, we know that the sum over n over these lambda n is finite. Furthermore, we have phi n and psi n, these are orthonormal systems, two orthonormal systems. And in this step number 3, I would like to prove that if we take x, a bounded linear operator on the Hilbert space, and a positive number a, then we can obtain the following estimate, the absolute value of the scalar product of f of 0 and a, exponential I u b x, exponential minus I u b, phi times phi. This absolute value can be estimated in the following way. I claim that we have the bound to pi and the norm of c in the trace class, and the square root of this times the operator norm of x times the norm of phi, this special norm here, times, and here we have sum over n, lambda n, and the integral from u to infinity over the absolute value of the scalar product of phi n with exponential minus I xb phi to the power of 2 dx, and the square root of this factor. Let me check it. Yeah, that's correct. That's estimate 4.4. And this is where we stopped last time. And I would like to continue here with the proof of this estimate to prove the estimate 4.4. We observe that that the left-hand side reads as follows. Let's do it here. Yeah, I used the definition of the map capital F. So the left-hand side reads as absolute value of the scalar product of the integral from 0 to a, exponential itb, exponential I ub x. Then we have the c, exponential minus I ub, exponential minus I tb phi, and integrated with respect to t, and this in the scalar product with the phi. This is exactly the left-hand side. Yeah. If you look back to the other blackboard, I have simply replaced here the definition of the map F0A, and then we find that this is exactly this formula or this term here. Yeah. Okay. What can we do here? I claim that this is equal to the absolute value of the integral from 0 to a, and then we have scalar product c exponential minus I t plus u b in the scalar product with x star, exponential minus I t plus ub phi dt. Yeah? So what has happened, first of all, I can write the integral sign in front of the scalar product. That has happened here. And then I have thrown these terms to the other side, and then we get the minus sign here. So first of all, we have the exponential minus itb here, and then minus iub. X to the other side gives the x star, and this term here is exactly remaining. Yeah, do you see this? I've simply thrown these terms to the other side of the scalar product as adjoint operators. Yeah, first of all this one, and then this one, then you get the minus sign here. It's here. And finally the x to obtain x star. And this term here is remaining. Okay, then I can plug in the representation of the operator C to obtain that this is equal to the absolute value sum over n in n, integral from 0 to a. Here we have the singular values lambda n, scalar product exponential minus I t plus ub applied to phi with phi n times scalar product exponential I t plus u b x psi n in the scalar product with phi, and this is integrated with respect to t. Yeah. Do you see this? Keep in mind that the operator C had the representation lambda n, phi n, psi n, and then you see that here in the first argument we obtain exactly this here. Yeah, the phi is missing here, sorry. We obtain exactly this. Yeah, simply use this representation, then you get the sum. I've pulled it in front of the integral sign, and here we have the singular values in the lambda n, and then you apply, then you take the scalar product of what is standing here with the phi n. This is exactly this. And then we have the function psi n in the scalar product with this second argument here. But then I can throw again the x star to the other side to obtain the x, and this to the other side to obtain this factor here. Clear? Okay. Then we can go on and can have the following estimate. First of all, I use Cauchy-Schwarz for integrals to obtain the following. Sum over n. Here I have the lambda n, and then I have the integral from, oh sorry, I've forgotten one step. We should do this before we apply the Cauchy-Schwarz inequality. First of all, we can change the interval of integration. That's clear. Sum n in n. Here, of course, I can integrate from u to u plus a, and then I can simplify this integrand to exponential minus I xb phi with phi n, and here we have x psi n, and again I throw this to the other side and I get exponential minus I xb phi, and this is now integrated with respect to x. Yeah, this is clear. Now I've simply changed the variables here. So this is no problem. And now I can use Cauchy-Schwarz for integrals, first of all, to obtain the following estimate. This can be estimated by the sum over n. n in n. Here I have the lambda n. And then I have, first of all, integral from u to u plus a, absolute value of exponential minus I x b phi in the scalar product with the phi n to the power of 2 dx, and the square root of this, and times integral from u to u plus a, and the same for the second argument here. So we have the absolute value of x psi n exponential minus I x b phi to the power of 2 dx and the square root of this. Yeah, this is simply the Cauchy-Schwarz inequality for integrals that I've used here. Yeah, and now I can use Cauchy-Schwarz for sums in the next step. This is also possible. So in the next step, we obtain that this can be estimated by, the lambda. You recall that lambda n is positive, so it can be written as square root of lambda n times square root of lambda n. And then I can associate one square root with each factor, and then I obtain here the following: sum n in n. Lambda n, this is the square root, this is the power of 2 of the square root of the lambda n. Yeah? And then the integral from u, and because this is an estimate, I can directly go to infinity of absolute value exponential minus I x b phi with phi n to the power of 2 dx, and the square root of this, I hope it's possible to read this, times sum n element n, lambda n, integral from u to infinity absolute value of x psi n exponential minus I x b phi to the power of 2 dx, and the square root of this. Yeah, so this is simply the Cauchy-Schwarz inequality for sums now, where I've written this as the square root of lambda n times the square root of lambda n, and each square root is associated with one factor, and then you see that we obtain exactly what I have written down there. Yeah, this is okay. Yeah, now we use lemma 4.19. So in view of lemma 4.19, you can look it up. We know that the integral over R of the absolute value of x psi n exponential minus I x b phi to the power of 2 dx, this can be estimated by, we have proved it there, 2 pi times the norm of x psi n to the power of 2, this is exactly the vector that is here in this first argument, times this triple norm of phi to the power of 2. You can look it up in lemma 4.19 that this estimate is correct. Yeah, but then we can go on. And find that, hence, we find that the sum over n of the lambda n, and here the integral from u to infinity of the absolute value of x psi n exponential minus I x b phi to the power of 2 dx, that this can then be estimated by the sum over n of the lambda n times 2 pi times the norm of x, the operator norm of x to the power of 2, because psi n is an orthonormal system, times the triple norm of phi to the power of 2. Yeah, but this here, as you can see, is directly the norm of C in the trace class. So this can be then written as 2 pi, the norm of C, the trace class norm, times the norm of x to the power of 2, times the triple norm of phi to the power of 2. And this already completes the proof of 4.4. Yeah, and then finally we come to step number 4, where we combine all the results that we had obtained so far. So step number 4, in this final step, we combine the results obtained so far. First of all, we observe that the norm of W of t minus W of s applied to phi. There's one bracket too much. Yeah, it's correct, like this. This to the power of 2. Of course, this is nothing but the scalar product of W of t minus W of s phi times W of t minus W of s phi. Yeah, this is clear. And now I can rewrite this in the following form. This is nothing but the scalar product of, here I take this operator and throw it to the other side, then I obtain the adjoint, W of t star times W of t minus W of s phi times phi. This is the first summand that we have. And then minus, and here the same with the W of s. So we obtain here minus scalar product W of s star, W of t minus W of s phi in the scalar product with phi. And it is clear that, okay, let's do it like this. Let's write down the minus sign here, that we can write this term as plus scalar product of W of s star, W of s minus W of t phi times phi. And then you see that both terms are of the same form, except that we have exchanged s and t. Yeah, but formally they are identical. And now we can use, let's continue here. Now we can use what we had in 4.3. You might recall it that we had an expression for terms of this involving this capital F, and this is then equal to the limit a to infinity, scalar product f of 0 and a, y of t and t minus y of t and s, phi, in the scalar product with phi for the first term, plus limit a to infinity, and now the same with s replaced by t. And then we have f of 0 and a, y of s and s, minus y of s and t, phi, times phi, like this. So that let's continue here. So that finally the difference in the norm, so the norm of w of t minus w of s phi to the power of 2 can then be estimated by the lim sub a going to infinity of the absolute value of the scalar product of f of 0 and a of y t phi times phi, plus the lim sub for a going to infinity of absolute value f of 0 and a, y of t and s, phi times phi, plus, two other terms, plus the lim sub for a going to infinity of the absolute value of f of 0 and a, y of ss, phi times phi, plus lim sub for a going to infinity absolute value of f and 0, f of 0 with indices 0 and a of y of s and t, phi. This is 4.5. These are the four terms that we obtain now. Okay, now we should go back to the definition of this y to continue here. By the definition, of y, and now I write it down in the variables q and r in order to avoid confusion with the s and the t here. I take new variables here. We find that this scalar product of f 0a of y qr phi times phi, this is nothing but, simply look back to the definition of this y, then you find that it is minus I times the scalar product of f 0a exponential I qb j star exponential minus I q minus r a c exponential minus I rb phi times phi. This is the first term plus I scalar product f of 0 and a exponential I qb c star exponential minus I times Q minus R, A, and then the J, exponential minus I RB, phi times phi. Yeah, I've simply plugged in the definition of the y, and now in terms of the variables q and r. Yeah, nothing more. And if I apply this to the 4 terms that we have on the left-hand side here, it's clear that we now get 8 terms. Yeah? Because each of these terms yields 2 new terms of this type, and they are all of the same form. Yeah? So that the right-hand side of 4.5 yields 8 terms of the following form. Yeah, of the form lim sub for a to infinity, absolute value of the scalar product of f0a of exponential I qb, j or j star, I will denote it like this. Yeah, this can be j or j star, exponential minus I q minus r, and then c or c star, that's denoted like this, exponential minus I rb, phi times phi. Yeah, so in view of formal correctness, let me explain this notation on the other blackboard. We have that Q and R are either S or T. We have that this J in brackets star is either J or J star, and similarly C in brackets star is either C or C star. And it's also important to note that, of course, this is also clear, note that the order of the J or J star and C or C star may be interchanged. Yeah, to sum it up, let's look back here. This notation simplifies, in some sense, what's happening. We have here either J or J star and C or C star, and it's also possible that the order of these 2 terms may be exchanged. Yeah, but in general, these 8 terms that we get from this estimate here are of this type. That's what I wanted to say. Okay. Yeah, but we can estimate these terms by 4.4, by estimate 4.4, any of the 8 terms can be estimated by the following way: absolute value of f of 0 and a of exponential I qb, j or j star, exponential minus I, q minus r, a, 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 exponential minus Oh, sorry, this is missing here. We should correct it. It's a simple spelling mistake here. Here the A is missing, of course. Yeah. And then we have here this second term, and then we have the C, or the C star, exponential minus I RB, phi times phi. This absolute value here can be estimated in the following form by the square root of 2 pi times the norm of C in the trace class, and the square root of this. Yeah, then we have the norm of J and the triple norm of phi, and then we have this term with the sum over n in n, lambda n, and here we can integrate over the minimum of q and r and to infinity. This gives an appropriate estimate of the absolute value of exponential minus I xb phi n to the power of 2 dx and the square root of this. This is simply the application of step number 3 to the object that we have found now. Okay. Again, I apply lemma 4.19 by virtue of lemma 4.19. First of all, we find out that the difference, that's the term with which we started, w of t minus w of s, applied to phi and the norm to the power of 2 of this object. This can then be estimated by 16 pi, the norm of C in the trace class, times the norm of J times the triple norm of phi to the power of 2. Yeah, you simply apply lemma 4.19 to this integral here. Then you can estimate this by, let's do it here. You can estimate this by 2 pi. And then we have the norm of the phi n to the power of 2, but this is equal to 1, yeah? Because it's an orthonormal system. Question?
Nominal square, isn't it?
Where? No. No, simply the j. Let's complete it, then you will see it. First of all, here I apply this lemma 4.19. Then we get here, first of all, this, and then the triple norm of phi to the power of 2. This is simply the application of this lemma 4.19 to this integral. Okay, then we know this here is equal to 1, because we have an orthonormal system. So this term is equal to 1. And then you get the square root of the power of 2 of this object. So you simply get the triple norm of phi. And here you also have the triple norm of phi. So you get it here to the power of 2. So this is correct. And then you get 2 pi, the square root of 2 pi times the square root of 2 pi is simply 2 pi, and you get it 8 times, so 16. This is also correct. And yeah, of course, what's remaining here is this sum over the lambda n, but this is the norm of C in the trace class. And we get the square root of this here times the square root here gives simply the norm of C to the power of 1. This is also correct. And then what's remaining is simply the norm of the j. So it's correct. Okay. Furthermore, furthermore, by lemma 4.19, there is a constant C0. There is a constant C0 so that the integral over R of the absolute value of scalar product exponential minus IXB phi times phi n to the power of 2 dx can be bounded by C0. Yeah, but this is exactly what we had seen right now for all n and n. So this is clear. Together with, yeah, that's what I wanted to show. I hope that we have enough free space here. Let's do it here. Together with the fact that the lambda n are positive, that the sum over n over the lambda n is finite, we can apply Beppe-Levy's monotone convergence theorem. So Beppe-Levy's monotone convergence theorem yields that the function that sends x, which is a real variable to the sum over n lambda n, absolute value of exponential minus I xb phi times phi n to the power of 2 is in L1. So it's integrable. This simply follows from monotone convergence. Yeah. And here we can continue on the other blackboard. First of all, I think I have forgotten to give one important number to my equations, so I state it again once more to repeat it also. We had this estimate here a few steps before. Exponential minus IRB phi times phi, and we found out that this can be estimated by 2 pi norm of c b1 of h, the square root of this, norm of j, triple norm of phi, and here we had the sum over n lambda n, integral minimum q and r to infinity, exponential minus I xb phi times phi n to the power of 2 dx, and the square root of this. If I have forgotten to give this estimate a number, it's 4.6. Maybe I've forgotten this. So also to get it again into the mind, I write it down here. And we found out on the other blackboard that in view of Beppe-Levy's monotone convergence theorem, the function that sends x to the sum over n, lambda n absolute value exponential minus I xb phi times phi n to the power of 2 is in L1. Okay, and now we can continue by Lebesgue's dominated convergence theorem. So by the dominated convergence theorem, the last factor on the right-hand side of 4.6 is arbitrarily small, so becomes arbitrarily small. Yeah, in the sense, yeah. Okay, yeah, we check this after the lecture. Okay, no problem. Using these two results here and Lebesgue's dominated convergence theorem, we find out that the last factor here on the right-hand side of 4.6 becomes arbitrarily small in the sense that the sum n in n, lambda n, integral over or from starting from the minimum of s and t to infinity over the absolute value of exponential minus I xb phi n to the power of 2 dx becomes smaller than some given epsilon whenever for t sufficiently large and s bigger than t. And this then completes our proof. Here we are done, because for large values of s and t, any of these 8 terms converges to 0. Yeah, this is a constant, this does not change, and this last factor converges to 0. And this happens in any of the 8 terms that we had. And so the norm difference of w of t minus w of s applied to phi converges to 0. And this was what we wanted to prove. So this here completes the proof of Pearson's theorem, and we can directly come to 2 applications. 2 applications of this theorem. First of all, theorem 4.25, which is the Cato-Rosenblum theorem. Which says that let A and B be self-adjoint operators with the fact that the domain of A is equal to the domain of B, and assume that A minus B is trace class, then the wave operators omega plus minus of A, B exist and are complete. Yeah, the proof is easy. It simply follows from Pearson's theorem when we said the operator J that is occurring in this theorem equal to the identity operator, then AJ minus JB is simply the operator A minus B, and then by assumption this is trace class. And if you look back to the definition of the operators that we had in Pearson's theorem, this AB, or omega plus minus of ABJ, this exactly turns to the usual Möller wave operators when we choose J to be the identity. So there's nothing to prove. from Pearson's theorem, thus we get that the wave operators omega plus minus A, B exist, but it's clear that this assumption is symmetric in A and B. Yeah, so it also holds true for the difference. And then we conclude that also the operators omega plus minus BA exist. And we had a proposition that shows that in this case, when both operators omega plus minus AB and BI exist, then we also get completeness. So there's nothing more to do. I will do it in a short form like this. Yeah? So this already completes the proof here. And then we can continue with theorem 4.26. Which is Kuroda and Berman's theorem. And it says, again, let A and B be self-adjoint operators in the Hilbert space H with the property that the domain of A is equal to the domain of B. And furthermore, now we assume that the operator B plus I to the power of minus 1 minus A plus I to the power of minus 1 is trace class. So now we have an assumption for the resonance, then the wave operators omega plus minus AB exist and are complete. Okay, let's look at the proof of this. The proof. The main idea of the proof is to apply, of course, Pearson's theorem with the operator J being equal to the resolvent of A plus I applied to the resolvent of B plus I. Yeah. An easy computation shows that AJ minus JB applied to phi, this is nothing but B plus I to the power of minus 1 minus A plus I to the power of minus 1 applied to phi. Yeah, this is not very difficult, so I would like to omit this step. You can do it on your own. Hence, we conclude that AJ minus JB, and if I take the closure of this operator, this is nothing but B plus I to the power of minus 1 minus A plus I to the power of minus 1, and this is then, by our assumption, trace class. Here I have to say that, of course, I do this computation for phi in the domain of A, which is a dense subspace, and then we obtain this conclusion here. Now we can use Pearson's theorem, and Pearson's theorem now says that the strong limits t to plus or minus infinity exponential ITA. And now here comes the J. And then exponential minus ITB PAC of B exist. Yeah, this is a direct consequence of Pearson's theorem. And now we now consider vectors of type B plus I phi for phi in the HAC space with respect to B as, and this is also not very difficult to see, as the subspace consisting of all elements of this type, B plus I phi, for phi in HAC of B, and of course also in the domain of B, is dense in HAC. Yeah, we consider now elements of this type, and it follows from the identity that B plus I to the power of minus 1 exponential minus ITB P AC of B, if I apply this to such an element, B plus I phi, then I can shift this operator to this side and again to this side by the usual properties of these objects here, and then these two cancel out, so that what we finally have is exponential minus ITB phi. Yeah, because phi is in the HAC space, so the projection then becomes the identity. So it follows from this that the strong limits let's continue here. I will denote them by lambda, capital lambda plus minus, by capital lambda plus minus of A. This is defined as the strong limit for t to plus or minus infinity exponential I ta A plus I to the power of minus 1 exponential minus ITB P AC of B, that these strong limits exist. Yeah. Is it clear? Let's look back here. We know from Pearson's theorem that this strong limit here exists, and if we apply it to vectors of this type, this computation here shows that the term that I had written down on the other blackboard exists. This term that I had denoted as lambda plus minus A, this exists. This is the consequence of what we had obtained so far. Now the compactness of A plus I to the power of minus 1 minus B plus I to the power of minus 1, because this object is trace class, together with together with lemma 4.20. If you don't recall what this says, it said that if you have some compact operator C and you apply it to exponential minus ITB phi, where this phi comes from this M of B space, this dense subspace of HAC of B, then this converges here to 0 for t to infinity, and phi was in this M of B. So the compactness of our resultant difference together with lemma 4.20 now says that yields that the strong limit for t to plus or minus infinity of a plus I to the power of minus 1 minus b plus I to the power of minus 1 exponential minus ITB p AC of b is equal to 0. Yeah, of course, we should add here, and I should add here and a simple approximation argument. Yeah, because this result here only holds for this dense subspace M of B, but then by approximation it's clear that we also get it on the whole space. Yeah, so the compactness of this difference together with lemma 4.20 that says this here then yields that this strong limit here is equal to 0. Thus the existence of the lambda plus minus of A implies that also the following strong limits exist. Lambda plus minus now of B that I define as the strong limits for t to plus or minus infinity. Exponential ITA, and now the resultant with the B, exponential minus ITB P AC of B exist. The last step, applying the operator lambda plus minus b to elements of the form b plus I phi. These are the elements that we discussed for phi and HAC of B. We conclude that from this here that the wave operators omega plus minus of A, B exist. Yeah, but again, our assumption is symmetric in A and B. Yeah, if you look back to the other blackboard, this assumption here is symmetric. Sorry, this assumption. Yeah, if I exchange A and B, then I again get a trace class operator. So this assumption is symmetric, and then I can do the same arguments when I exchange A and B, and then I obtain that also omega plus minus BA exists. And by this proposition, I think 3.19 that we had. Yeah, 3.9, sorry, this implies that then the wave operators are also complete because both omega plus minus A and B and A exist. So this completes then the proof. Finally, I would like to consider a typical application of theorem 4.26. So let us consider finally an application. Let us consider a typical application of theorem 4.26. This example 4.27 here I take H0, which is minus Laplace. I usually define it on CC infinity. Here I'm in R3, and then I take the closure and let H be the operator H0 plus a potential V, where this potential V should be in L1 and bounded. And my goal now is to prove that we show that H0 plus 1 to the power of minus 1 minus the resolvent of H, that this operator is trace class with respect to the Hilbert space L2 of R3. Yeah, and then we can apply the theorem 4.26 to obtain that the wave operators omega plus minus of H and H0 exist and are complete. And as you can imagine, this is of great practical importance. Yeah, so to obtain the existence and completeness for this typical setting with Schrödinger operators, you simply have to check that this difference here is trace class. And this is not very difficult. So that by theorem 4.26, we will conclude that omega plus minus of H and H0 exist and are complete. Okay, what can we do? We can use the resolvent equation to argue as follows. I take this resolvent difference here for the difference corresponding to H and H0. This is by the resolvent equation simply, the second resolvent equation simply this. Now here in the middle you have the difference between H and H0, and this is simply the potential, so you get this. And now you can proceed as follows. This is H0 plus I to the power of minus 1 V. And here we have H0 plus I to the power of minus 1, plus H plus I to the power of minus 1 minus H0 plus I to the power of minus 1. So I have simply added in 0, as you can see. But this yields that we have here H0 plus I to the power of minus 1 V h0 plus I to the power of minus 1. This is a term which is here symmetric in the sense that both components include the h0. And here we obtain that this is nothing but h0 plus I to the power of minus 1 v. And this here can again be replaced by what we found right there. So this is h0 plus I to the power of minus 1 v h plus I to the power of minus 1. This is 4.7. And in the final 5 minutes, we will comment on the behavior of these two summands that we had obtained here. And we find out that, first of all, from standard theory, the operator h0 plus I to the power of minus 1 has an integral kernel. This follows from standard Fourier analysis. Has an integral kernel, let's say g of x and y, such that we have the estimate that g of x and y is bounded by 1 over 4 pi exponential minus absolute value of x minus y over x minus y. Yeah, this follows from Reed and Simon, volume 2. This is standard. Yeah, and then we conclude that if I apply the operator absolute value of v to the power of 1/2 to h0 plus I to the power of minus 1, then this has an integral kernel, let's say gv of x and y, satisfying with the property that gv of x and y is simply bounded by 1 over 4 pi absolute value of v of x to the power of 1/2 exponential minus x minus y over x minus y. And then one shows that this GV is in L2 on R3 times R3 because of the following, because of the following observation. Let's do it on the other blackboard. Yeah, so simply let's compute the integral over R6 of GV of x and y to the power of 2. That's what we want to show. This is then bounded by 1 over 16 pi to the power of 2, and then I get an integral for the x variable like this, and here an integral over R3 with the terms to the power of 2, including x and y. In this sense, yeah, but it's clear that you can use polar coordinates here and the usual transformation formula to conclude that this integral here is finite. Yeah, you simply use a transformation of variables to obtain that this is simply this here. Like that. And then using polar coordinates, you see that this inner integral exists. So this is nothing but C0 times the integral over R3 over the absolute value of x dx. And we assume that V is an L1 function, so this works. We conclude that the operator absolute value of V to the power 1/2 times H0 plus I to the power of -1, this is Hilbert-Schmidt. Yeah, because the integral kernel GV corresponding to this operator is in L2. So we have a Hilbert-Schmidt operator here. And then in consequence, we find that the operator H0 plus I to the power of -1 V square root V square root H0 plus I to the power of -1 is a trace class. Simply from the fact that the product of two Hilbert-Schmidt operators is trace class. Yeah, here we have the adjoint of this object, and the Schatten-von-Neumann classes are ideals. So this is again a Hilbert-Schmidt operator. This is Hilbert-Schmidt, and then the product is trace class. Yeah, what do we also know? Let's look back to the formula where we started. As V H plus I to the power of -1 is bounded, this is a bounded operator, and as B1 of L2 of R3 is an ideal, the second summand on the right-hand side of 4.7 is also trace class. Yeah, let's look back to the other blackboard to understand this. So first of all, we had discussed this term here. Yeah, let's look back to the other blackboard. This is exactly this term here. Yeah, and we found out that this is a trace class operator. This is the first term here. So here it's clear that this object is trace class, and then I said that this operator here is bounded, and we know this operator here is a trace class operator. And by the property that the trace class is an ideal, we conclude that if we apply a bounded operator here, then the whole object is again trace class. Yeah, so this whole right-hand side is a trace class operator, and this is exactly what we wanted to show. And then we can apply a theorem 4.26 to obtain that the wave operators for this setting exist and are complete. Yeah, this is what this example shows. There's a final remark in the script. I will not write it down now because of the time. You can find it in the script when I have loaded it into the internet. In the next lecture, I would like to present an example. I would like to discuss a situation with a one-dimensional potential, and I would like to compute the wave operators and the scattering matrix and any object that occurs in this setting explicitly.